All right, everyone. I am logged in and I am against this background that will make my face impossible to discern, but I am about to start up a tablet that I will use to annotate the test. All right, so yes, you may record this, and I should also be recording this. Let me just a sec. Adrian, is there something wrong out there? What? Okay. Let me just double check that this is being, yeah, this is being recorded right now. All right, so what I plan to do is just go over last semester's final exam because the spirit of this one will be similar. Anything that was important enough to be on the final exam is probably important enough to be on the final exam this semester as well. It's basically the same topics. So this first question is a question about waves on a string going from x equals 0 to x equals 90 centimeters. And the ends of the string are fixed so that the displacement is 0 at both ends. And it tells you where there are antinodes. And there are several ways to write such a wave. We have to figure out which one is correct. Well, the way I would approach a problem like this is I would start by sketching the string. We've got x equals 0, x equals 90. And we know that there are antinodes or peaks at x equals 45. So there's a peak in the center. Then there are peaks at 75 and 15 centimeters, peaks or troughs. I'm just drawing this as a peak. I know that the next antinode, if this one was a peak, the next one must be a trough because the waveform has to look something like that. So x equals 45, and then there's going to be nodes here and here. So this is going to be at 75 centimeters. All right, so somebody tell me what the wavelength must be. Because if we know the wavelength, we can immediately start ruling out some of these k values. What must the wavelength be? Well, let's see. We know that between one antinode and another, there's a node, and it's going to be halfway in between. So this is 45 and this is 75. Then that must be 60 centimeters. That must be 60 centimeters. So this looks like the wavelength here. So right away, I can rule out, That's not what I intended to do. Okay, so right away, I can rule out this one. I can say that that's got the wrong wavelength. Now, the others have the right wavelength, so I'm going to have to think more about it. One thing I know is that it has to have an antinode at x equals 0. So I can rule out some of these, like, for instance, or let's see, I can rule in some of these possibly. If I look here, all right, if I look here, I've got a function that is always 0. Oh, wait, but that one's already been ruled out. If I look here, I've got a function that is always 0 at x equals 0, because I could factor out the e to the I omega t. As a matter of fact, let's factor out the e to the I omega t from all of them. If I look here, I've got e to the I kx, e to the minus I omega t, minus e to the I kx, e to the plus I omega t. So this one I can't factor out that time dependence. Okay? I can't factor out the time dependence. This one is a function of kx minus omega t. And that's a problem because that means that the nodes are traveling. So I can immediately conclude that this one is wrong. The nodes travel. It's not a function of x times a function of time, because if it were a function of x times a function of time, then we could potentially have it so that it is always 0 when t equals 0, but we don't have that. Now, let's look at this one. If I look at this one, I've got e to the minus I omega t in the first term, and I've got e to the minus I omega t in the second term. So I can write this as e to the minus I omega t times e to the I kx minus e to the minus I kx. And this is equal to 0 at x equals 0. So this one's valid. This one is a sine function, and it's valid. Any questions? This last one, although I wrote it differently, and now, right, there's no easy way. Editing in here is not easy. There's no easy way to undo this. This one again is e to the minus I omega t times e to the I kx minus e to the minus I kx. It may not look like e to the minus omega t because there's a plus omega t there, but it's multiplied by a negative I. And this is also equal to 0 at x equals 0. Any questions? Now, since writing waves out in terms of complex numbers is an important thing in this class, I'll just say right up now that there will be a problem that involves picking expressions for waves in terms of complex numbers. I don't promise it'll be like this one. It might be like the one from the first midterm. Sorry, from the second midterm where you had to deal with electromagnetic waves. But one way or another, there will be some sort of problem that involves formulas for waves in terms of complex numbers. So I would suggest studying this problem, studying the first midterm, studying the second midterm. There will be something that looks like that. Any other questions? All right, let's go to the second one. Energy density. All right, so how much energy is in this system? And in this case, we were given E and B, and we know that the energy density is 1/2 epsilon naught E squared plus 1/2 mu naught B squared. All right. Now, energy is conserved. In this case, energy is sloshing back and forth between the E field and the B field, but energy is conserved. It's the same at all points in time. So if I calculate the energy at one moment in time, I know the energy at any other moment in time. And in this case, plugging in t equals 0 would make things really easy, because the B field is just 0 at t equals 0, and the E field is E naught x hat sine squared pi mz over L at t equals 0. So I think I'd like to work with that one. All right, I think I would like to plug in t equals 0. So in that case, it's just going to be 1/2 epsilon naught E naught squared sine squared pi mz over L. So the energy would be the integral of that. 1/2 epsilon naught E naught squared sine squared pi mz over L dz. So that's just going to be, well, now we have to use a trig identity, which was given somewhere at the beginning. Here, we are going to use this identity. Sine squared is just 1 minus cosine of 2 times whatever variable you're working with. So that will be a 1/2 times another 1/2 times epsilon naught E naught squared integral z equals 0 to L 1 minus cosine 2 pi mz over L dz. Now, the integral of dz is just z. All right, so if that, we're going to get a 1/4 epsilon naught E naught squared z. That's the integral of the first term. The integral of the second term, well, let's see here. The derivative of sine is cosine, or cosine is the derivative of sine. Sine of 2 pi m z over L, evaluated from 0 to L. And remember that L over 2 pi m comes from using the chain rule when we take the antiderivative of cosine. Now, the first term is really easy. We're just going to get 1/4 epsilon naught E naught squared times L minus 0. And the second term, let's see, we're going to get sine of 2 pi m L over L. And what's the sine of 2 pi or 4 pi or 6 pi or 8 pi? This is a sign that you should know.
0.
Thank you very much. And then we're also going to get the sine of 0, which is just 0. So this goes away. and we're left with something very easy. L over 4 epsilon naught E naught squared. Since I had a problem like this on each of the midterms, I'm going to have a problem like this on the final. I'm not going to tell you which of those two it will be, and maybe I'll put some sort of little subtle spin on it, but basically you'll have an expression for the wave inside of a system, and you're going to have to integrate it. You should practice doing integrals like this. These are integrals that are worth practicing because they show up all over the place in physics. I mean, I'll tell you now that what I'm doing, there is a method to this madness. I'm doing this because you're going to need to see it again. I'm not going to ask you to do things on a final exam that you won't see in any future class. I'll only ask you to do things that show up in other areas of physics. Questions? So practice integrating squared trig functions. Now, in this case, we've got 4-slit interference. We've got 4 slits on the screen, and we have to add up the fields from those 4 slits. And there was something like this on the midterm. And so basically what you need to first do in any problem like this is, 1, pick a reference point. Usually the center of the screen is easiest. And then 2, start adding. I'm going to zoom in a little bit here, no pun intended. And we are going to pick our reference point from the center of the screen. So R naught will be the distance from the center to the screen. So the first distance is going to be y equals d over 2, and then down here, y equals minus d over 2. All right? And then down here, we're going to have y equals minus 3d over 2. And up here, we're going to have y equals plus 3d over 2. That's important. On the midterm, some people got confused as to where the reference point was. If it's from the center of the screen, then the distance is not d sine theta, but d over 2 sine theta, or minus d over 2 sine theta. Once we've got that, then we can start adding. You can say that E is proportional to E naught, e to the I, k r naught, times e to the I, k d over 2 sine theta, plus e to the minus I, k d over 2 sine theta. Oh, but there are masks in front of the 2 middle slits, which delay light slightly. Forgot about that detail there. So if we give something a half cycle delay, then this one should get a minus sign, because when you go through half a cycle, you go from peak to trough. So this should have a minus sign there. So when we put all of that together, then what do we get when theta equals 0? When theta equals 0, all these exponents are 0. And e to the 0 is 0, so we've got -1, -1, +1, +1 if theta equals 0. Any questions? There's no rule that we have to have either that if we put a mask over it, the phase shift has to be exactly half a cycle. The math gets easier if the phase shift is half a cycle, but we could easily have a quarter phase shift, a quarter cycle phase shift. If it's a quarter of the way through the cycle, oops, sorry about that, we would multiply by e to the I k times lambda over 4, which is e to the I times 2 pi over lambda times lambda over 4. The lambdas cancel, the 2 cancels partially. We're left with e to the I pi over 2. Anybody know what e to the I pi over 2 is? Cosine pi over 2 plus I sine pi over 2. Pi over 2 is the same as 90 degrees. And what's the cosine of 90 degrees? 0. Sine of 90 degrees is 1, and so we're left with just I. There's no guarantee that will give you a problem. Well, first of all, there's no guarantee you'll have a phase shift. I want you to prepare for all the possibilities. You could just have a few slits with different distances to add up. You could have a few slits with different phase shifts. Those phase shifts might not always be either a half a cycle or 0 cycles. Those phase shifts could be a quarter of a cycle. Or I could tell you, hey, we put something over it that gives a phase shift that is unknown. You're going to have to calculate it. And then I'll say to you, hey, I want the field at such and such angle to be a maximum or to be a minimum. And you'll have to figure out, all right, constructive or destructive interference, what kind of phase shift should I give this? Any questions? Okay, now we come to relativity. So let's see, we have 3 mirrors that are stationary with respect to each other and the lab. Oh, and by the way, I don't promise that these will be the only types of wave or optics problems on there. I can also have something that involves a diffraction grating or a lens. All of those are important. All of those show up in future classes. But there will be 3 or 4 wave and optics problems, and there will be 2 or 3 relativity problems for a total of 6 or 7 problems altogether. I haven't finalized it yet. Okay, so 3 mirrors that are stationary with respect to each other and the lab. And we are told what the horizontal spacing between the 2 bottom mirrors is, 8 nanoseconds. Delta Y is 3 nanoseconds. And light goes from A to B to C. And so we are asked to find all of the space-time intervals. Well, space-time interval is always equal to delta t squared minus the distance squared. So from here to here, this distance is going to be, well, let's see here. This is 4 nanoseconds. So this is going to be 5 nanoseconds because it's a 3, 4, 5 triangle. All right? And we know that for light, the distance traveled equals, for light going in a straight line, the distance traveled equals the time. So let's see, delta S AB. Well, it travels a distance of 5 nanoseconds. It takes 5 nanoseconds to go that far. So that's 0. Light lives in the eternal now. Light is always convinced that nothing has yet happened and that anything could change. Light is the most optimistic thing in the universe. And likewise, to go from here to here, well, that's a distance of 5 nanoseconds. And it takes 5 nanoseconds. But now, to get from here to here, to get from A to C, that's going to be the square root of, let's see, 5 nanoseconds this way, 5 nanoseconds that way. So 10 nanoseconds squared minus 8 nanoseconds squared, or the square root of 100 minus 64 nanoseconds. Any questions?
Yeah, can you explain one thing? Can you explain why the previous two are 0 again?
Why the first two were 0? Because delta TAB is 5 nanoseconds. It was light going from there to there, and then light going from there to there. So light takes a time of 5 nanoseconds to travel a distance of 5 nanoseconds. If I didn't have light, let's say that instead of, let me start a new drawing, different color. Let's say I have a high-speed neutron going from one to the other. Okay, well now, delta TAB is 5 nanoseconds over the speed. All right? So delta SAB would be the square root of 5 nanoseconds over V squared minus 5 nanoseconds squared, because it's always time squared minus distance squared. So that's going to be 5 nanoseconds square root of 1 over V squared minus 1. Questions?
Thank you.
Other questions? All right, so we're told in problem 5 that we got a light beam going up and to the right, makes a 60-degree angle with the x-axis according to an observer in the lab. So in the lab frame, this is what we've got. Second observer is going along the x-axis. And they also see the light going to the right. So this is in the home frame. But then we've got this other observer going with velocity beta. And they say that the light beam is only making a 30-degree angle with the axis. All right, remember, people can disagree on the velocity of light. They can't disagree on the speed of light, but they can disagree on the velocity of light. All right, so we need to somehow figure out what is beta. Any suggestions on how we would do that? Anyone? Well, have I told you what the velocity components are in the two frames? I mean, on one level, of course I haven't. I haven't said the words Vx equals this many meters per second, Vy equals that many meters per second, Vx prime equals this other number of meters per second. I obviously haven't done that. But I've given us some information on Vx and Vx prime. All right, Vx must be cosine of 60 degrees, which is 1/2. Vy must be sine of 60 degrees, which is square root of 3/2. Vx prime is cosine of 30 degrees, which is √3/2. Vy prime is sine of 30 degrees, which is 1/2. And by the way, I didn't put any relativity formulas on the formula sheet, but I will put some on the formula sheet this time. One formula that I would give you is that Vx prime would be equal to Vx minus beta over 1 minus beta Vx, and Vy prime would be equal to Vy square root of 1 minus beta squared over 1 minus beta Vx. Well, it looks to me like if I were to, I could pick either of them. I don't want to mess around with square roots if I don't have to. If I just take this one, looks to me like I was given Vx and Vx prime. All I need to do is solve for beta. So let's do that. √3/2 equals 1/2 minus beta over 1 minus beta over 2. And then I just have a linear equation to solve. So I will multiply both sides by 1 minus beta over 2, and I'm going to get √3/2 minus beta √3/4, because I multiply beta over 2 by √3/2 equals 1/2 minus beta. All right. Then I can just go √3/2 minus 1/2 equals beta √3/4 minus 1. So finally, beta is equal to √3/2 minus 1/2 over √3/4 minus 1. Any questions? I feel like I did something wrong there. So let me pull up my solutions from last year, or last semester. No, looks like I did that correct. Yeah, I think the only thing that I did wrong here is that I assumed when I wrote this down that the other observer was moving to the right. But now let's think about this. One person says that the person in the home frame says that the light is making an angle of 60 degrees with respect to the axis, which means that Vx must be pretty small. If the other observer is moving to the right, that would make Vx even smaller. Okay, but we know that they see an angle of 30 degrees, which means that they see a larger value of Vx, all right? So they must be going to the left, all right? They must be going to the left so that if the light beam is to the right of them, you know, if they're, let me see in Zoom, all right? If the light is going like this and the person's going like that, all right, then they need to see the light making a shallow angle so that it's going away from them mostly horizontally, all right? That would make sense. On the other hand, if the other person was going like that, then they would see the light moving it to the right more slowly. It would be moving kind of parallel with the light, sort of. They'd be moving closer to parallel with the light, and so they would see the velocity of the light be mostly upward. I know I'm not stating that very well. It's hard to make statements about relative velocity of light that are simultaneously, what just happened? Share that screen. It's hard to make statements about the relative velocity of light that satisfy the simultaneous constraints of being both intuitive and accurate. Any questions on that? Okay, so I can promise you that with relativity, there will be something that in some way involves definitions of time. And if I only have two problems, then if I have three relativity problems, there will be a distinct relative velocity problem. If I only have two problems, then I'll mix relative velocity in with something. But I'll tell you that definitions of time are important. It's what you need in order to learn general relativity. Relative velocity is important. And then finally, particle decays, energy, and momentum. I mean, that's where relativity really gets used. If you use relativity in your career, then it is very likely that you would use it in the context of something like that. So let's look at this last problem. This last problem involves neutron decay. And neutron decay is a big deal in physics right now, simply because the experiments don't agree with each other. They've done two different, we know that neutrons decay. If you leave a neutron alone, then after about 15 minutes on average, it will decay into a proton, an electron, and an antineutrino. We know this. But people have done these experiments under different conditions. And when they do these experiments under different conditions, they get different answers, which could mean that there's something really weird about the physics of decaying neutrons. That would be really amazing. It would mean that the fundamental laws of physics have some surprises for us. More likely, it means that somebody has made a subtle error in how they interpreted the experimental results. You know, were they forgetting to correct for something in the way they measured the decay rates? But that is why it's a hot topic in physics right now. And so I put it on the final. Now, if I were to put neutron decay on it, I'd have to put some sort of different twist on it this time. I can't just give you the exact same problem photocopied. But it is entirely possible that it will be a neutron decay problem. It will definitely be something that involves conservation laws. So let's work through that. We've got a neutron decaying into a proton, electron, neutrino. let's consider the case where the neutrino's energy, momentum, and mass are negligible. And sometimes that's the case. Then we could ask, what are the kinetic energies of the proton and electron? All right. So if we assume that P nu bar equals 0 and E nu bar equals 0, then we just have that the mass of the neutron is equal to the energy, because initially this neutron was standing still. And that's got to be equal to the energy of the proton plus the energy of the electron. And the momentum of the neutrino was 0, which is going to be equal to the momentum of the proton plus the momentum of the electron. Right now, we've got two equations here. We've got 4 unknowns. But for starters, we know that these two add up to 0. So we can immediately deduce that the momentum of the proton is minus the momentum of the electron. So we won't have to carry around 2 different momenta. So Mn is equal to EP plus EE. And we need some more equations here. Any suggestions for something that we could use to add some more information?
The E squared minus P squared equals M squared.
Yep. So we could use that. All right. And what we could immediately do then is that we could set this equal to the square root. Alternately, we could write that E is the square root of M squared plus P squared. All right. That's something else that we could do. Or we could say that the square root of E squared minus, you also say that P is the square root of E squared minus M squared. This gets a little awkward with the minus signs. So maybe it would be better to say that P squared E equals P squared P equals all right. So we could rewrite all of this as E squared P minus E squared E equals M squared E minus M squared P, right? Because I subtract the P squared, E squared P from both sides and add the M squared E to both sides. And what I get is that EP plus EE times EP minus EE and what do these two have to add to? Just look at the page. Above it, we know that these two add up to the mass of the neutron. So we've got that the difference of these two energies is equal to this difference of squared masses over a neutron mass, and their sum is equal to the neutron mass. So now we have two equations and two unknowns. When in doubt, always try to get things into a difference of squared energies or a difference of a squared energy and a squared momentum. Always try to get into a difference of two squares, because the difference of two squares is something that we can factor really easily into a sum multiplied by a sum of two variables multiplied by a difference of two variables. So if I put these two equations together, if I add them, I get that 2 times the proton energy is equal to the neutron mass plus so I subtract those, and I don't really have more room to write. But once I've got this, then I could plug in some numbers with my calculator. And then I could just say that E sub E is equal to the neutron mass minus E sub P. Now, those will give me the energies. But if we look at the problem, what I specifically asked for are the kinetic energies. So how do I go from having the energies of the electron and proton to having the kinetic energies?
The kinetic energy equals E minus M, and we found E's already. So, and we have the M as given, so we just plug it into that.
Yep, exactly. Other questions? Well, I'll tell you right now what I'm going to do, and then we've got more time for me to be available and answer questions. I'm going to post this commented PDF of last semester's final exam. And when this is over, and I'm going to post that on Blackboard, I'm going to post the recording of this session on YouTube. The other thing that I'm happy to do for the next 28 minutes is take questions on any homework assignment or previous midterm that you wish to discuss. So if nobody has questions on this, then why don't you just give me a couple minutes to post this file on Blackboard, and you use that time to go through your old homeworks and problem sets and midterms and whatever. And in a couple minutes, I will ask about that. Post an announcement. All right, what else do people like me to go over? Well, let's see who else is logged in. Lots of people are logged in. Does anybody have a homework problem you want me to go over?
Professor, can you go over problem 2 in problem set 13?
Problem set 13, problem 2.
Yes.
All right, let me open up a notepad here. Just a sec. All right. So problem set 13, problem 2. All right. So the Cylons and the 12 colonies have established a truce demarcating a boundary in space. Battlestar Galactica is sitting in colonial space at x equals 0, 6 light minutes to the right of the boundary, i.e. the boundary is at x equals -6. Suddenly a Cylon ship passes by Galactica, speeding towards the boundary at 3/5 the speed of light. Okay. So we want a diagram showing all of these things. All right, let me go into the solutions. So I'm going to move those solutions to something that I can open on my other device. And is sharing still on? No, somehow sharing has been turned off again. Share my screen. Okay. So, did you look at the solutions already? All right, so first we need a diagram showing the world line. So Galactica is standing still. So Galactica's diagram should just be, oops, now I gotta go into here and mark it up. Okay. So Galactica is standing still. So its world line is just stationary. The Cylons are moving at a rate of 3/5. So basically, in a time that it looks like they would travel a distance, if they are going at a rate of 3/5, x equals minus 3/5 t, t equals minus 5x over 3. So when x is 3, then, or x is minus 3, then t should be 5. And indeed, that looks to be the case right there. Okay, actually, let me just do something with that. There is a way to do these in different colors. That is indeed the case. So that's the Cylons. And then we are told in the problem that they fire a gamma ray blast at the speed of light at t equals 5 on Galactica's clocks. So when we are there at t equals 5, we see that red line going with a slope of 1. Any questions on that part?
No.
All right, so t equals 5 if x equals minus 3. All right, then we need to find the position and time of each event in the reference frame of the Cylons. So we're going to have to use these two formulas. X prime is gamma x minus beta t, t prime is gamma t minus beta x. All right, and at that point, it just becomes a plug and chug exercise. So I started off with the event coordinates in the home frame. Then I plug and chug and get the event coordinates in the Cylons frame using these two formulas. If you want, I can go through each event in the table. Was there a specific one you want to know about?
No, I just wanted to know how you like set the problem up, but then I kind of got it how you showed the world lines.
Okay. Other questions?
Professor, I have a question on D. Like, it's more of a conceptual question, but so if there was a third ship to both witness C and D happening, wouldn't that ship have to experience simultaneity? And in order to do that, he has to be like in the same distance apart, like from C.
No. There's a difference between receiving light from two events at the same time and saying the two events happened at the same time. Let's say that tonight I simultaneously see a flash of light from an ambulance going down the street and I see some light from a distant star. Both flashes of light reach me at the same time, but I know that that distant star emitted that light tens of thousands or even millions of light years ago, depending on where that star is. All right, so receiving two flashes of light at the same time, seeing two things at the same time, is different from saying that they are simultaneous in my reference frame. Conversely, let's suppose the two things are simultaneous in my reference frame. Then ambulance here in Pomona emits a flash of light, and that an ambulance in Seattle emits a flash of light. And I have some super powerful telescope so I can see that flash of light from Seattle, or I get a radio wave from that ambulance in Seattle. I will not receive them at the same time. I will receive the light from the ambulance in Pomona before I receive the light from the thing in Seattle. But I could use my information to say that these two things were emitted at the same time in my reference frame. And it keeps turning off sharing. Other questions? Anyone? Anyone? I'm thinking of watching Ferris Bueller's Day Off for my birthday coming up soon. Bueller. You know, the actor who did that famous line is Ben Stein, and I actually won $850 of Ben Stein's money. Do you guys know who Ben Stein is or what his game show was? Probably not. Ben Stein is, well, he's been a lot of things. He's an actor, a writer. At one point, he worked for a president. And in the early 2000s, he had a game show on Comedy Central called Win Ben Stein's Money. And it was a quiz show. It was like a comedy version of Jeopardy. And I won $850 on there. And it keeps turning off sharing for some reason. But he was also the actor in Ferris Bueller's Day Off who asked those famous droning on questions trying to get people to answer questions or participate in class. So that is a cult movie for my generation. And then like 15 years after, roughly 15 years after he made that movie, I went on his show and met him and won some of his money. Any questions at all on other homework problems, midterm problems?
I had a question, but it's not on like a problem. How long are we gonna have to do the final exam?
You're going to have 3 hours. I'm going to make it available at 8:30, and it will be due at 11:30.
Okay, thank you.
Other questions?
Professor, will your office hours during final week be the same?
Yeah, pretty much, and I'm available at any other time too. So, you know, if you need to talk to me, I mean, even if it's not office hours, generally I'm not going anywhere this week. So at most I might be out hiking in the hills near my house, but I'm always home within an hour. So if you email me within an hour, you should get a reply. And once I reply, once I'm at home and able to reply, then I can be in front of Zoom and take your questions right away.
Okay, thank you.
You're welcome. All right, well, if there are no other questions, then I'm just gonna sign off and post this video on YouTube. Have a good day and have as good of a summer as you can under the circumstances.